Good afternoon, everyone. My name is Bottieau Jérémie, and I am a PhD student at the University of Mons, more particularly at the Power System and Market Research Group. And it's my pleasure to present you today our work named A Distributionally Robust Framework for Improving the Provision of Passive Balancing Services. The first questions we may ask is, what is passive balancing services? Passive balancing services refer to intentional deviations of market actors from their energy positions to support the real-time system balancing. The services typically take place in European markets where the single price imbalance settlement is applied. Typically, here during the imbalance settlement period, you have a positive system imbalance. The TSO, the transmission system operator, must activate downward balancing bits to offset this system imbalance. The activation costs are covered by applying at each unbalanced market actor an imbalanced price. Here, if you provide passive balancing services, you have two choices. You can be in excess of production compared to your schedule. In this case, you will aggravate the system imbalance and you will be paid at a negative price. Or you can consume more than your scheduled. Here you will reduce the system imbalance and you will pay a very attractive price for this excess of demand. And our objective of this work is to support the decision-making process of market actors that provide this passive balancing service. We see in the previous example that if an actor adopts a short position, it will be beneficial for him and for the system. But if the market actor adopts a too short positions, it will change the sign of the system imbalance, and here in this case, it will pay a very high price for its excess of demand. And to take into account this regime switching behavior of the imbalance price, we rely on a bi-level methodology, where the upper level maximizes the profit of the market actor that provide passive balancing services, and the lower level problem simulates the imbalance pricing mechanism. So our model needs two types of inputs. The first one is the representation of the future system imbalance. This is made here by scenarios, which are obtained by sequence-to-sequence recurrent neural network. The second type of input is the price quantity curves of the activation of balancing reserve. These price quantity curves can be published by the European transmission system operator in order to promote a more transparent and more competitive market. So our tool will optimize the imbalance position of the market actor in expectation over an imbalance price distributions. And this imbalance price distribution is obtained through multiple imbalance pricing mechanisms which take into account the imbalance position of the market actor and the system imbalance scenarios. Here, the main novelty of our work is to apply distributionally robust optimization on this framework. Distributionally robust optimization considers a family of imbalance price distributions and will optimize in expectation over the worst case imbalance price distribution inside this family. So this framework will allow us to take into account the fact that the uncertainty of the future system balance cannot be perfectly captured by our model. To assess the performance of our model, we perform an out-of-sample analysis using real-world market data from the Belgian power system for each quarter hour of the 2 months periods. So I illustrate the result using only one figure, but other results are available in the paper. Here we see the three optimization techniques: distributionally robust optimization in blue, scenario-based stochastic programming in orange, and robust optimization in green. And the main message of this figure is that when your representation of your uncertainty is not complex enough, here which is represented by a too few number of scenarios, you really see the added value of applying distributionally robust optimization, where you see a higher expected of sample profit and it allows the market actor to make better informed decisions. So, to conclude, this paper aims at supporting the decision-making process of a market actor that provide passive balancing services. So to do so, we develop a distributionally robust bi-level optimization tools, which has two benefits. The first one is that it allows to hedge against the regime-shifting behavior of the imbalance price. And the second benefit is that it allows to take into account the fact that the uncertainty representation of the future system balance cannot be perfectly captured by our model, and to be more robust against that. We assess our tool on a realistic case study based on the Belgian power systems, and the outcomes demonstrate the added value of using distributionally robust optimizations, especially when you have a representation of the uncertainty too simplistic, which is here represented by a too few number of scenarios. Thanks all for your attention.